Good morning, professors. I'm Lao Chenpeng from Carmel Secondary School. My team registration number is 90049, and my research topic is zero-knowledge mutual authentication in the two-party password-authenticated key exchange setting. Future goal, a mission impossible. Why would I choose this as my research topic? Before this research, I wanted to send a love letter to my girlfriend. The letter was very private, so I didn't want my classmates to read what I'd written about. Nor would I let my girlfriend know my own password, since it would be very troublesome for me. Also, I didn't want to rely on a third party to communicate with her. Therefore, a 2PAKE setting with zero-knowledge characteristic, or a ZK2PAKE scheme, is needed. In this project, I've defined some of the notions and aims in a 2PAKE setting. Then, I discussed the minimum pre-shared information, or a PSI, required. After that, the explicit authentication phase in the scheme is explored. For any ZK2PAKE protocol, it should achieve two aims. First, both clients should not be able to obtain their partner's passwords. Second, no third-party trusted server shall be included in any phase of the protocol. In my hypothesis, my initial hypothesis is that it is impossible to implement zero-knowledge in any 2PAKE setting. I've defined the following symbols as on page 4 of my report. Note that H is a one-way hash function, while F is the one-way compression function. I've also included the following definitions about functions on page 4 of my report. And then define the following terms on zero-knowledge on pages 4 and 5 of the report. Note that if a protocol is ZK, it is a secure protocol. I also made the following assumptions on page 5. First, I assume that all passwords are human memorable, and the client should remember one and only one password for all sessions for him. Then, I assume that all encryption algorithms are perfect. Let's look at the PSI requirement. I assume that the passwords, usernames, and multiple random numbers are the only strings that can be used to generate a PSI. And then consider 6 general cases. In case 1, the PSI is solely determined by the client's own password. An illustration of the flow in this case is shown here. I assume that it is possible to mount a brute force attack here because it requires 2 to the power 32 computations only. However, I've proved that the protocol is vulnerable to impersonating attack, which is more catastrophic than exhaustive searches. Also, the scheme is vulnerable to collision impersonating attack, in which Alice may use Bob's PSI as her own PSI with Cindy. Then, Alice may switch her role between herself and Bob by using the same PSI but different usernames. Obviously, case 1 is very unsafe. In case 2, the PSI is computed by the client's own password and username. Unfortunately, I proved that the addition cannot increase cryptographic protection, since this causes no variation in the resulted PSI, or in other words, the number of elements in the sample space equals 1. By this, case 2 is not more secure than case 1 by any means. How about adding the partner's username? In case 3, the PSI is generated by the client's own password and the partner's username. While in case 4, the PSI is further modified by the client's own username. However, I've proved that the adversary can mount brute force attack in these protocols, since the attack requires 2 to the power 32 computations only. By this, it's obvious that the two cases are insecure. After the unsuccessful trials, I wonder whether adding random numbers can solve the brute force attack problem. In case 5, the PSI is created by a fixed number of random numbers and the client's own password. I've derived that the number of computations to generate a PSI is equal to 2 to the power d plus nx, where d is the dictionary size of the password, n is the number of random numbers included, and x is the number of bits of these random numbers. Obviously, Tn is non-polynomially bounded. By this, we can obtain a corollary that the successful probability for a passive adversary, which is the reciprocal of Tn, is negligible when n is large. Hence, the protocol in case 5 can be considered a secure one. Unfortunately, the security of the generation of PSI still lies on the client's own password. Why would I say so? In case 6, the PSI does not depend on the client's password, and it can be shown that the protocol is vulnerable to privacy leakage by a corrupt oracle. Hence, the protocol is again insecure. But as a roundup, it is not impossible to implement mutual zero knowledge in the pre-shared round of a 2-PAKE setting, as what we have seen in case 5. We now turn to the explicit authentication process. This is divided into two main parts, which are one-round and multiple-round authentication. In a one-round authentication without any timestamp, I proved that message replay attack is possible, and the inclusion of random numbers cannot increase cryptographic security, since it is impossible to check the freshness of these numbers. Hence, the protocol is unsafe. However, using timestamps may allow mutual computation of zero-knowledge properties. I've derived that in optimum conditions, the completeness probability equals 1, the soundness probability is less than 2 to the power negative d minus nx, and it is computationally indistinguishable for an adversary to identify the randomly encrypted timestamp from the honest one, because the advantage is negligible. This fulfills the requirement of computation of zero knowledge. We now move on to the multiple round cases. First, we consider the challenge response mechanism, where the prover uses the hashed PSI to encrypt multiple values specified by the verifier. However, this cannot reduce the soundness probability during authentication. Also, the running time can be non-polynomially bounded, so the protocol is not computational zero knowledge. However, I've proposed a generalized conjecture which was intuitively proved. In this conjecture, for any cryptographically secure 2-PAKE protocol with its running time polynomially bounded, an encryption key only constitutes the PSI but not the password itself, the protocol may become computational zero knowledge. In my intuitive proof, a simulator simulates the transcript by computing the random PSI by hashing the random password and n random numbers. So the advantage of the verifier is smaller than 2 to the power negative d minus nx. This approaches to 0 when n is large. By this, we obtained the generalized argument that phi is computational zero knowledge. In conclusion, ZK2-PAKE protocol is theoretically possible to be implemented in the real world. My initial hypothesis is therefore rejected. As a discussion, I found that ZK2-PAKE setting is an interesting and new concept, and it may even substitute the problematic 3-PAKE after extensive researches. Therefore, this topic is worth studying in the future. This is the end of my presentation. Thank you very much.